Hello and welcome to our talk, Are measurements of fluctuating wall shear stress with flush-mounted cavity hot wires possible? By Adalberto Perez, Alex Alvisi, Alessandro Talamelli, myself Ramis Örlü, and Philip Schlatter from KTH Stockholm, Sweden and the University of Bologna, Italy. Before we go over to the fluctuating wall shear stress and its measurements, let us recapitulate how the near wall region of wall-bounded turbulent flows scales. The underlying idea of classical inner scaling is based on the empirical observation that the streamwise mean velocity is solely a function of the wall distance when scaled with viscous units. While the exact analytical description of the law of the wall is not known from theory, this is not the case when considering the immediate vicinity of the wall, that's to say, the viscous sublayer. A Taylor series expansion at the wall yields that the inner scaled mean velocity is a linear function of the wall distance. The Reynolds number similarity, or independence, has also been shown to be valid for the immediate vicinity of the wall when considering the RMS of the streamwise velocity component. A Taylor series expansion at the wall also here yields a directly linear relation to the distance of the wall. Considering the local relative turbulence intensity in the region where the Taylor series expansion describes the data well, it can easily be shown that the relative turbulence intensity approaches a constant value in the limiting case where the wall distance tends to zero. This constant behavior could for a long time not be observed experimentally due to both spatial resolution effects and even more so due to additional heat transfer effects when using thermal anemometry probes. Nonetheless, this issue was settled upon the seminal work by Alfredson et al., showing that the relative turbulence intensity approaches a value of about 0.4, irrespective of flow case and Reynolds number, where this value corresponds to the RMS of the fluctuating wall shear stress. While most of our understanding was based on experimental evidence, the emergence of direct numerical simulation data of canonical wall-bounded flows confirmed the law of the wall. Variance profile exhibits an increasing amplitude with increasing Reynolds number. This also implies that the RMS of the fluctuating wall shear stress related to the relative turbulence intensity has to increase. Having established that the fluctuating wall shear stress magnitude is increasing with Reynolds number, be it for internal flows such as channels or semi-confined flows such as turbulent boundary layers, DNS could be utilized to demonstrate that the near-wall small-scale motion is indeed universal, that's to say, it scales in inner units, as apparent from the 2D spectra of the fluctuating wall shear stress. The Reynolds number dependence, however, observed in the RMS profiles and the fluctuating wall shear stress, is found to be a manifestation of the large-scale structures and their imprint on the near-wall region. Hence, the RMS of the fluctuating wall shear stress can be expressed by a constant related to the small-scale energy as well as a Reynolds number dependent term related to the large-scale structures. While all DNS from internal flows and turbulent boundary layers seem to have established that the fluctuating wall shear stress is increasing with Reynolds number, the present study is motivated by a recent study by Gubian et al., in which the authors utilized a flush-mounted hot wire sensor installed over a tiny cavity in order to eliminate the additional heat transfer effects otherwise encountered with such probes and thereby benefit from the high frequency response of hot wire sensors compared to hot film sensors. A surprising result from the study, as stated in the abstract of Gubian et al., was that the turbulence intensity of the fluctuating wall shear stress increases monotonically with Reynolds number and asymptotes to a value of 0.44 for a friction Reynolds number of above 600. Since the experiments by Gubian et al. Are performed in a turbulent channel flow, the results are rather surprising, recalling that the amplitude found by Gubian et al. For these low Reynolds number is way too high when compared to turbulent channel flow simulations. Above all, the DNS indicates a clear Reynolds number trend for Reynolds numbers way higher than encountered in the experiments. Obviously, these experiments are also at odds with our correlation for the fluctuating wall-shear stress for zero pressure gradient turbulent boundary layers. The first thing that came to our mind as a possible explanation was that this could be an artifact of the insufficient spatial resolution of their hotwire probe. However, Gubian et al. Were confident that their sensor gave no indication of reduced spatial resolution as the Reynolds number increases. Faced with this contradicting finding, we have shown in a recent comment to their paper that one could recover the Reynolds number dependent increase of the fluctuating wall-shear stress if one would account for the insufficient spatial resolution of their hotwire probe. Although the amplitudes are strongly overestimated, the Reynolds number trend is clearly recovered. While the overwhelming evidence from the literature is clear about the Reynolds number trend of the fluctuating wall-shear stress, the authors are confident about the results. Hence, we wanted to go back and try to understand what the problem might be. In particular, in light of the assumptions for the cavity probe, which seemed to rely on the assumption that any disturbance to the surrounding flow due to the presence of the cavity itself is negligible. This assumption was made since there are no detailed studies in the literature dealing with the flow inside the cavity that is so small as employed for cavity hotwire probes. To address this gap in the literature and to understand the results by Gubian et al., we addressed this issue with two master thesis projects. One experimental by Alvisi, in which we wanted to replicate the measurements by Gubian et al. In a low Reynolds number turbulent boundary layer, both with the cylindrical cavity as used by Spassini et al. And the rectangular cavity as used by Gubian et al. Additionally, in order to get an idea about the flow field around the cavity and be able to map the parameter space, a DNS in a low Reynolds number channel flow has been performed, in which the cavity was simulated by means of an immersed boundary method with different length and depth, recalling that the underlying assumption of cavity probes is that any disturbance to the surrounding flow due to the presence of the cavity itself is negligible. Let us first consider the center plane of the cavity. Considering the mean velocity profile compared to the black line which indicates a channel without cavity, it is clear that the mean velocity above the cavity is slightly enhanced. The root mean square of the fluctuations are even more enhanced. Hence, the amplitude of the fluctuating wall-shear stress, which is the limiting value of the relative turbulence intensity when approaching the wall, is strongly increased. Considering now a specific cavity size of a depth of 9 inner units and a streamwise length of 50 inner units, and comparing our DNS with our experiments, it is clear that the presence of the cavity enhances the relative turbulence intensity by around 45% for both the DNS and experiments. This can more clearly be observed when considering the contour plot of the relative turbulence intensity around the cavity. A smooth wall would exhibit a fluctuating wall-shear stress magnitude of around 0.4, while the presence of the cavity clearly enhances this value upstream, downstream, and above the cavity. While this cavity size is larger than the one employed by Gubian et al., Considering smaller cavity depth down to 3 viscous units, which corresponds to the highest Reynolds number case of Gubian, it is apparent that the overestimation of the fluctuating wall-shear stress can still account for around 20–30%. Coming back to our comment paper on Gubian et al., in which we anticipated that their measured values are strongly attenuated due to insufficient spatial resolution, we can now compare the overestimation of 20% with our simulations. Considering now the same cavity size as in Gubian et al., we can see that our simulations indicate an overestimation of the fluctuating wall-shear stress of 20%, which is identical with our estimations. Hence, their probe measured actually the correct amplitude, but the flow they considered is not a canonical turbulent channel flow, but a turbulent channel flow influenced by a tiny cavity. To summarize, we have shown that cavities as small as 3 viscous units can drastically disturb the flow around the cavity. We have also demonstrated that the results by Gubian et al. Are strongly attenuated due to insufficient spatial resolution effects, which explains their observed asymptotic state. These results show that the fluctuating wall-shear stress is substantially overestimated when sensed with a hot wire probe embedded in a cavity. While this could have been the end of our presentation, the authors responded to our comment by drawing our attention to 3 DNS studies of zero pressure gradient turbulent boundary layers. Apparently, these studies indicate that the evolution of the fluctuating wall-shear stress with Reynolds number is hardly a settled matter. In particular, they state that the fluctuating wall-shear stress magnitude appears to become a constant and asymptote to a value of 0.44 at a high Reynolds number. However, considering the cited DNS datasets, we can state the following. First, the DNS by Sayadi et al. Does not exhibit a constant value of 0.44. Instead, it agrees perfectly with our correlation, which exhibits a clear Reynolds number trend. Second, the DNS by Wu and Moyne exhibits indeed a higher amplitude, however, it asymptotes towards our correlation. Second, the DNS by Wu and Moyne indeed exhibits higher amplitudes, as we have also shown in our inflow and tripping papers due to post-transitional effects, but their amplitudes converge on our Reynolds number dependent trend. Third, the DNS by Koyatse has known streamwise convergence issues and thus too high values of the fluctuating wall-shear stress, but yet a clear Reynolds number trend. Hence, all DNS agree on the Reynolds number dependence of the fluctuating wall-shear stress. And this is the end. Thank you for your attention. All mentioned references can be found in our latest comment paper on the study of Gubian et al.